Welcome to Math with Professor V. In this video, I'll be solving the entire exam that was just given to my Calculus 2 class spring 2025. It covers integration techniques, approximate integration, improper integrals, surface area, arc length. All right, let's jump right in. 10 questions. Integrate the function. We have y squared over 36 minus y squared, all raised to the 3/2 dy. Find the integral. So first thing you want to think through, what are my options for integration techniques? And I usually go, can we do u sub first? And then if u sub doesn't work, which in this case it won't, then I start thinking, okay, maybe by parts, and then trig sub, and then partial fractions, etc. Go through the checklist in your mind. So this is just going to be the perfect time to use trig sub. I know this is to the 3/2, not your typical square root, but it's fine. It's going to work out just as beautifully. So if you look at this expression here, that's being raised to the 3/2, since we have the constant first minus the variable quantity. Remember, when you have a squared minus y squared, and you're going to do trig sub, you let y equal a sine theta. So in that case, we're going to let y equal 6 sine theta for this problem. Then we need to find dy, that's the next step, which is going to be 6 cosine theta d theta. And then let's go ahead and rewrite the whole integral in terms of theta now. So in the numerator, instead of y squared, I'm going to have 6 sine theta squared, okay, over 36 minus another y squared. Are you guys good if I just write 36 sine squared theta? And then this is all to the 3/2. And then instead of dy, now what do we have? Well, dy is 6 cosine theta d theta. Okay, fabulous, fabulous. All right, so let's see what's going on. Up top, I've got 36 sine squared theta. And then you know what? Let me just put times 6 cosine theta right next to it. D theta is going to go right here. And then always remember, when you do trig sub, the point is to simplify this using one of our Pythagorean identities. So we factor that 36 out, and then we have 1 minus sine squared theta, and then that's all being raised to the 3/2. So now in the denominator, we can say we've got 36 cosine squared theta raised to the 3/2. Beautiful, beautiful. Now let's simplify further. So we've got integral. Just to kind of help you simplify more easily and not deal with such big numbers, this is 6 squared times another 6. Now I have 6 cubed up top. 6 cubed. And then we have sine squared theta, cosine theta, d theta. And then here in the denominator, 36 to the 3/2, if you need a refresher, it means take the square root of 36 and then raise it to the 3rd. So that's also going to give you 6 to the 3rd. It's 216, but just in case you didn't know that off the top of your head, let's leave it as 6 to the 3rd, no problem. And then here, if we're simplifying cosine squared raised to the 3/2, you multiply these exponents, 2 times 3/2, so the 2 cancels. So then we're just left with cosine cubed theta. Okay, beautiful. So look at that. The 6 cubed, 216, is gone. This cosine theta cancels, and then now I'm just going to have 2 in the denominator, 2 of them. So I've got sine squared theta over cosine squared theta d theta, which is tangent squared theta. D theta, don't forget the d theta. Now, do we know antiderivative of tan squared theta? Not right off the top of our head. We have to use another Pythagorean identity and replace tan squared theta with, that's right, secant squared theta minus 1 d theta. Now we can take the antiderivative of both those terms. So antiderivative of secant squared theta is tangent theta, minus antiderivative of 1 is theta, and then we put plus c. Now we're not done. Remember, the original integral was all in terms of y, so we have to get back there. How do we do so? It's triangle time. That's right. So right here where you made your trig sub, y is 6 sine theta. That means y over 6 is sine theta. I'm going to use that to draw a triangle. Draw a right triangle. Put your angle theta somewhere. And then make sure that sine of that angle, sine of theta, is equal to y over 6. So that's the ratio of the opposite side over the hypotenuse. Now the missing side here is square root 36 minus y squared. And you should have seen that missing side appear somewhere in the original integral. We do. Square root of 36 minus y squared. This is the same as square root of 36 minus y squared cubed, right? We could just write it to the 3/2 instead and it looks a little better if you ask me. So yep, there it was. Okay, now we use a triangle to go back to y. So we have our answer in terms of y. So tangent of theta is going to be ratio of opposite over adjacent side. So that's going to be y over square root 36 minus y squared minus, and then when you have plain old theta, you need to use the inverse trig function and just come back to where you made the substitution as well. To isolate theta, I would just take sine inverse of both sides. So theta is sine inverse of y over 6 plus c, and then we're done. Okay. Very good. Very good. So that was the first one. Now let's look at another one involving approximate integration. Find an upper bound for, this is the magnitude of the error using the trapezoidal rule, when we're estimating the integral from 2 to 5 of 1 over x minus 1 squared dx with n equals 4 steps. So the formula for the upper bound on the error when using the trapezoidal rule to approximate an integral is that the error is less than or equal to k times b minus a cubed over 12n squared. And k is an upper bound on the second derivative of the function, the integrand, on the interval from a to b. It's an upper bound on the absolute value of that second derivative. Okay, so all we need to do is figure out this expression, this quantity, and we'll be answering the question here. Hopefully you can identify everyone that's going on. So here's A, here's B. F of x, the function, is 1 over x minus 1 squared. And then they already told me n is 4. So the only thing I'm missing, right? So I've got b and a and n. I need to find k. This is always tricky for students. So k is an upper bound on the second derivative, yes? So let me take two derivatives and then we'll talk about it. So before I start, let me rewrite this as x minus 1 to the negative second. So then f prime of x is going to be negative 2 times x minus 1 to the negative third. And then we need one more, so f double prime of x is going to be 6 times x minus 1 to the negative fourth. So you have a couple options. I need to find an upper bound on the absolute value of this second derivative. Now the absolute value of f double prime, it's already positive, right? So nothing's going to change. I want to know what's an upper bound for 6 over x minus 1 to the fourth on the interval from 2 to 5. And there's two ways you could do it. One is just by reasoning. I have a constant in the numerator and a variable expression in the denominator. This is going to be the biggest it ever is when the denominator is the smallest that it could possibly be on the interval. So I know for sure this is always less than or equal to 6 over, what's the smallest x can be? 2, minus 1 to the fourth, which is just 6. I know for sure on this entire interval that the absolute value of the second derivative is always less than or equal to 6. Because as x gets bigger, 2, 3, 4, 5, the denominator gets bigger, so this whole quantity gets smaller, smaller, smaller. So you could just do that by reasoning since we have no variables up top and only the denominator changing. If that makes you nervous, here is another option. We want to know when is f double prime of x at its max, right? Finding an upper bound isn't exactly the same as finding a max, but if we find the max, that also serves as an upper bound. So we could find the max of f double prime of by looking at its derivative, f triple prime. So remember in Calc 1 when you were trying to find local extrema, so the local min or local max of a function, you looked at its derivative, right? To see its critical values, etc. So if I take a third derivative, then that's going to be negative 24 over x times x minus 1 to the negative fifth, which is negative 24 over x minus 1 to the fifth. So no, I don't take the absolute value of this. What I observe is that on the interval from 2 to 5, this denominator is always positive. This is a negative quantity. So this third derivative is always less than 0. What does that mean? That means f double prime is decreasing on the interval from 2 to 5. So what would that look like? Well, I don't know exactly what f double prime's graph looks like, but it's decreasing from 2 to 5. This is f double prime. So that means it attains its max when x is 2. So then to find k, to find an upper bound on the second derivative, you just plug in 2 for x. Okay? Good. The maximum, the actual max value that it attains, that's its least upper bound. But also 10 is an upper bound, 20 is an upper bound. But those are not the least upper bounds on the second derivative. And you don't want to overshoot too much because then your error approximation, the upper bound on your error, doesn't tell you as much information, right? Like I could tell you I'm less than 100 years old, but that still doesn't give you a very good idea of my age, right? But if I tell you I'm less than 45 years old, oh, okay, then now you can kind of like pin things down a little bit more. So you have, an infinite number of upper bounds on this second derivative, but the tighter or the closer that you get to the least upper bound, the true max, the more helpful that is in giving you information. Anyways, I probably should just make a whole video on this topic. I digress. Let's just get this show on the road and answer the question, right? So I'm just going to use this formula right here. Don't fret. Error from trapezoidal rule is less than or equal to k, which is 6, times b minus a, so 5 minus 2 cubed, over 12 times n is 4 squared. So then this is 6 times 27 over 12 times 16. And then I can cancel this 6 and the 12. This is 2. And that's all that I can cancel. So 27 over 32. Okay, good. That's the final answer. Since I've boxed a few things and I want this to stand out, I will also box it with highlighter. Ooh, that's right. Okay, moving on. Use Simpson's rule with n equals 4 steps to estimate the integral. So we're going from negative 2 to 2, antiderivative of x squared plus 3 dx. Now we don't need to use Simpson's rule. We could easily just evaluate this guy, but we're just practicing that we know the rule. So the interval's from negative 2 to 2. That's A, that's B. Let's find delta x first, which is b minus a over n. Look how nice I was. 2 minus negative 2 over 4, no fractions. So then I like to draw out and partition the interval before I set everything up. So we're going from negative 2 to 2, 4 subintervals, pretty easy, right? Those are all my x values at which I'm going to evaluate the function for Simpson's rule. And then you just got to remember the setup. So Simpson's rule with n equals 4 is delta x times 1/3 times, and then we would have 1 times f of negative 2 plus 4 times f of negative 1, and then it alternates the 4's and the 2's. But it always goes 1 and then 4 first. 2 times f of 0 plus 4 times f of 1 plus f of 2. Good? Okay, well, delta x is just 1 times 1/3. F of negative 2 is 7. 4 times f of negative 1 is 4. Plus 2 times f of 0 is 3. And then these values repeat, right? Plus 7. And then from here, you'll get 1/3 times 14 plus 32 plus 6. So what was I doing? I just added the 7s together. And then these are 2 16s. And the 6, I don't know, just works better in my brain. And then I was like, oh yeah, 14 plus 6, that's 20. 20 plus 32, there's 52 over 3. Thank goodness addition is commutative, right? Beautiful. Okay, one more. Estimate the minimum number of subintervals needed to approximate the integral from 0 to 1 of 18 cosine x dx with an error of magnitude less than 10 to the negative fifth using Simpson's rule. Okay, so in this case, I gave them also the formula for the error bound for Simpson's rule. It's a little different than trapezoidal. Notice k is an upper bound on the fourth derivative of the function whose integral we're approximating. And then we have b minus a to the fifth and 180 n to the fourth in the denominator. You can see you're going to get less error, right, for the same n because you have n to a higher number. And then this is also a larger constant. Okay. So first let's find k, because pretty much everything else is given, right? Can you identify who's going on? This is b and a. We need to find n, so estimate the minimum number of subintervals. We're finding n. And we need this error, so we need k times b minus a to the fifth over 180 n to the fourth to be less than 10 to the negative fifth. Okay, so let's find k. K is an upper bound on the fourth derivative. So f of x is 18 cosine x. Let me take 4 derivatives. It won't be bad though. So f prime is negative 18 sine x. F double prime is going to be negative 18 cosine x. F triple prime is going to be positive 18 sine x. And then at long last, my fourth derivative is what I started with, 18 cosine x, not a coincidence. So what's an upper bound for this fourth derivative on the interval from 0 to 1? Well, I know absolute value of 18 cosine x. Cosine x is always less than or equal to 1. So this has to be less than or equal to 18 on the interval from 0 to 1. So that's my k. And I don't need to do anything more than that. Okay, so we've got k now. K is 18. So we have 18 times 1 minus 0 to the fifth over 18 n to the fourth is less than 10 to the negative fifth. And then no, there's no calculator, so they got to solve this. So, oh, this should be 180, excuse me. 180 n to the fourth. Okay, so 18 over 180, that cancels. So I have 1 over 10 n to the fourth is less than 10 to the negative fifth. I'm going to multiply n to the fourth over to the other side. So then I just have 1/10 is less than n to the fourth times 10 to the negative fifth. This is the same as 10 to the negative first. Okay. Are we good with that? Yes, we are, Professor V. Okay, perfect. And then to get rid of 10 to the negative fifth, you multiply by 10 to the positive fifth. 10 to the positive fifth. Okay, then we'll have 10 to the fourth is less than n to the fourth. Take the fourth root, n has to be greater than 10. Now in Simpson's rule, n has to be even. So if n has to be greater than 10, you would round up to 11, but then we have to skip 11 and say n has to be greater than or equal to 12 for our final answer, in order to make sure that we have an error magnitude less than 10 to the negative fifth. Okay, good. That was a little spicy point because you have to remember for Simpson's rule, n must be even. For the other two rules, I would have just rounded up to 11. Okay, good. Moving on to question 3. Evaluate the integral from 0 to natural log of 3 of e to the x dx over the square root of e to the 2x plus 1. Okay, so this one, I had them practice it in class a couple times. You're going to do a u sub first and then a trig sub. Some people are comfortable, they can just go straight to the trig sub right away, but most of my students mess it up if they try to do that because, when you first learn trig sub, you're probably not super professional at it. So I'm going to break it down in 2 steps. But if some of you guys notice how to just go straight to the trig step, good. Do it that way. All right. I'm going to give you a hint, though. You need to think of e to the 2x as e to the x squared. Okay? So that's how we're going to get that u sub going. We're going to let u equal e to the x. And then du is e to the x dx. And see, we have e to the x dx right there. And then that can just be my u squared. Then we do have to change the limits of integration. These belong to x, so I need to change them to limits in terms of u. So u of 0 is e to the 0, which is 1. And then u of ln of 3 is e to the ln of 3, which is 3. So those are my new limits. Okay, you can't leave the old ones. Everything has to match, otherwise it's not well defined. So we have 1 to 3 du over square root u squared plus 1. Okay, so make sure you change your limits. These belong to x. These need to belong to the variable of the integral u. You can't just stop writing limits and say, I'll go back to them later. No, this is a definite integral. You can't make it indefinite now. You have to maintain the integrity of what the problem was that was given to you. This represents area under a curve, right? If you just stop writing it, then it represents something different. So you have to have respect for the math, okay? Good. Now we do trig sub. So we have a square root, all right, and then u squared plus 1 tells me it's time to do the substitution that involves tangent theta. So we're going to let u equal tangent theta. Then du is secant squared theta d theta. And then again, we have to change our limits. So always ask yourself, who do these belong to? What variable? These belong to u. So I'm going to plug them in for u. These guys belong to u. I know that because there's u's over here. So that means 3 equals tan theta and 1 equals tan theta. Now I need to solve for theta. You don't plug those values in for theta, no. So theta is tan inverse of 3, which we don't know off the top of our head. 3 is not one of the numbers that comes up on our unit circle. And then also theta equals tan inverse of 1, but yes, we know this is pi over 4. Okay, so we're going to write out our integral now. It's going to go from pi over 4 to tan inverse of 3. Instead of du up top, I have all of this. Secant squared theta d theta. Beautiful. Over square root u squared plus 1 is tan squared theta plus 1. Good, good. Okay, and then anytime you do trig sub, use your Pythagorean identity. So this is secant squared theta. And then we have square root of secant squared theta, which is secant theta. Technically, it's absolute value of secant theta, but we restrict theta. It's positive here on this interval. So if all of that is secant theta, it's going to cancel with one of the secants up top. And then now we just have pi over 4 to tan inverse of 3, secant theta, d theta. Do you know antiderivative of secant theta? That's one you should just put to memory. ln absolute value, secant theta plus tan theta. And then we're going to evaluate this from pi over 4 to tan inverse of 3. Okay, good. So then we have ln absolute value, secant of tan inverse of 3 plus tangent of tan inverse of 3 minus ln absolute value secant of pi over 4 plus tangent of pi over 4. Okay, now how do you evaluate something like secant of tan inverse of 3? If you're in trig right now, you're going to remember. If you haven't done trig in a minute, I'll remind you. So anytime you see some inverse trig function, remember that represents an angle. Tan inverse, sine inverse, secant inverse, those are all angles, thetas. That's a theta. So if theta is tan inverse of 3, that means tangent of theta is 3, which is also 3 over 1. I'm calling it 3 over 1 because that's right, it's triangle time. So here we go. Theta, opposite over adjacent, tangent of theta is 1, hypotenuse is rad 10. So now can you use this sweet little pink triangle and tell me what is secant of theta? So secant of theta would be reciprocal of cosine theta, which would be hypotenuse over adjacent. So rad 10 plus, well, this is just lovely. This is just going to be 3, right? Tangent of tan inverse of 3 minus ln secant of pi over 4 rad 2, tangent of pi over 4, 1. And then hopefully you observe everything's positive, so we can just switch to parentheses. We don't need to keep these absolute value bars. You could combine them into a single logarithm if you're inclined. I'm not inclined, so I'm just going to box this and be done. Okay? Very good. All right, next problem. We have definite integral from 1 to 4, square root of y times natural log of y dy. So what technique do you think is appropriate here? U sub won't work, but I always think about it first because it's the first integration technique you learned. It's the least messy, so always check. But no, it won't work. It's a beautiful time for by parts because we have the product of two functions. One of them involves a natural log, so yeah, by parts. How should we pick u and dv? So when you have natural log, that needs to be u because we don't know the antiderivative of natural log off the top of our heads unless you memorized it. But you need, in order to get the antiderivative, you do integration by parts. So logarithms, I would say like almost 100% of the time are u when you do by parts. And then dv is going to be everything else. So rad y dy, which I'm going to think of as y to the 1/2 dy. Okay? Then let's find du. So that's 1 over y dy. And then v, antiderivative of y to the 1/2 is 2/3 y to the 3/2. All right, good. So then let's use our by parts formula. So this is going to equal uv. Now, since this is a definite integral, be careful. So we're going to have 2/3 y to the 3/2 ln y. That doesn't go under an integral. We don't integrate that. But we do have to remind ourselves to evaluate it from 1 to 4. So you need to write that there. Minus, and then the integral of v du. Let me take that constant out. So 2/3 integral from 1 to 4 of 1 over y times y to the 3/2 dy. Are we good? We're great. Okay, perfect. So 2/3 y to the 3/2 ln of y from 1 to 4 minus 2/3 integral 1 to 4. No, you don't need to do integration by parts again. You can just simplify this. Y to the 3/2 divided by y to the 1st is y to the 1/2. Okay, so now we have 2/3 y to the 3/2 ln y. And then since I'm already ready to take the antiderivative here, I'm not going to write this part. I'm just going to at the end put brackets from 1 to 4 for everybody. That's how I like to do it. I think it makes it neat. Minus 2/3 times another 2/3 y to the 3/2 from 1 to 4. Are we good? Okay, perfect. Now, let's plug in our upper and lower limit. So we've got 2/3 times 4 to the 3/2 times ln of 4 minus 4 over 9 times 4 to the 3/2 minus, and then this is going to be 2/3 times 1 to the 3/2 times ln of 1. Ooh, that's going to be good. Minus 4/9 times 1 to the 3/2. Okay, so this is going to be 2/3 4 to the 3/2. It's square root of 4. You take the denominator root of that number, so square root of 4, and then you raise it to the numerator, to the third. So 2 to the third is 8. And then ln of 4 minus 4/9 times, this is again 8, minus, since this is 0, this is all 0, plus 4 over 9. Are we okay? All right, good. So then this is 16/3 ln of 4 minus 32 over 9 plus 4 over 9. And then we're nearly done. So 16/3 ln of 4, that's 16/3 ln. To completely simplify, that's 2 squared. Minus, these guys give me 28 over 9. And then you can move this exponent to the front. And we have 32/3 ln of 2 minus 28 over 9. Okay, good. So anytime that base is a prime power, you should want to rewrite it in terms of that prime number raised to some constant and then move it in the front, just to simplify as much as possible. Okay, now we get into some improper integrals, which is tricky, I think, for most students because it involves not only integration, but also limits. So that can be a lot for some people. So evaluate the improper integral or state that it's divergent. So we have integral from 0 to infinity, e to the negative square root of x dx. So in this case, you can't do u sub and be done, but we are going to do u sub and then something else to get the ball rolling. Okay, so this is going to require multiple integration techniques, not to mention the fact that it's an improper integral. So the absolute first thing we need to do is rewrite it with the limit. So I'm going to say this is the limit as t goes to infinity, integral 0 to t, e to the negative square root of x dx. Okay, so now let's do u sub. I'm just going to let u be the square root of x. You could throw the negative in there as well, but I'd just rather not. I need to take the derivative, but before I do that, let me just square both sides. It'll be easier. So u squared is x, and then now differentiate both sides. So 2u du is dx. And then we do need to change our limits of integration because these belong to x. I need them in terms of u. So u of 0 would be square root of 0. That stays 0. And then u of t is square root of t. And you're just going to leave it like that, okay? Just deal. So we've got now limit t goes to infinity, integral 0 to square root of t. This is e to the negative u. And then instead of this dx right here, I've got 2u du. Let me put 2u in the front, du here. Cute, huh? Okay, from here, I recognize I'm going to need to do integration by parts because u sub won't work. And if I have some polynomial function, 2u is a polynomial. It's not a very exciting one or spicy, but it's a polynomial. Times exponential, you need to do by parts. It's a great time to do tabular. I recommend it because you're less likely to make a mistake or have to introduce new variables. We already used up u, so you would need to pick something else when doing tabular. I mean, if you're not doing tabular, excuse me. So the exponential function always goes under I, just like how you would pick dv. In fact, some of my students were saying they just call this u and dv because it's the same thing, but you know. Here's 2u. Now let's keep taking derivatives till we get 0. So 2, 0, that was quick. And then antiderivative of e to the negative u is negative e to the negative u, and then one more. And then we take our diagonal products, and then don't forget to alternate the signs. I started putting the pluses and the minuses out here instead of above the arrow like I used to, copying my students. They did this, and I'm like, oh, that looks so much less squished. I love it. Okay, so we're done. So don't forget to keep writing limit. T goes to infinity. And then we'll have, so this product here, don't change the sign. It'll be negative 2u e to the negative u. And then we have minus, so add that extra negative, 2e to the negative u. And this is evaluated from 0 to square root of t. Okay, now we substitute in our limits of integration. So limit t goes to infinity, negative 2 square root of t e to the negative square root of t minus 2e to the negative square root of t minus negative 2 times 0 times e to the 0 minus 2e to the 0. I need limit of all of that. I think it's helpful when you have a negative exponent and you're trying to figure out the limit, rewrite that in the denominator as a positive exponent. It'll just help your brain see what's going on better. So limit t goes to infinity, negative 2 square root of t over e to the square root of t minus 2 over e to the square root of t. That's just 0. And then this is going to give me, that's right, plus 2. Okay. Let's go from right to left, order of easiest to hardest when we're taking the limit. This is a constant, so that's just going to 2. If t goes to infinity, square root of t goes to infinity, and e raised to something getting large gets very large also, so this whole term goes to 0. If you have a constant over the denominator approaching infinity, it goes to 0. Now the next one, we know this denominator is going to infinity, and then t is going to infinity, so this whole numerator is going to negative infinity. So we basically have negative infinity over infinity, which is an indeterminate form. So we need to do L'Hopital's rule to evaluate the limit off to the side. So you just take a little moment for yourself and you go aside. Or you could write consider. The limit as t goes to infinity of negative 2 rad t over e to the rad t. So I verified we've got negative infinity over infinity. So we can go ahead and use L'Hopital's rule. Limit t goes to infinity. So derivative of negative 2 rad t, leave the negative 2. Derivative of rad t is 1 over 2 rad t over, and then derivative of e to the something is e to the something, and then I have to do the chain rule. Derivative of rad t is 1 over 2 rad t. Okay, that's good, because these 1 over 2 rad t's cancel. And then we don't have to do L'Hopital's rule again. We just got limit, t goes to infinity. Can you see what didn't cancel? Good. Negative 2 over e to the rad t. So then the denominator is going to infinity. We have a constant now in the numerator, so this goes to 0. So then I could say, okay, this term here goes to 0. So all I'm left with is 2. Well, what do I care about the fact that my limit was 2? This tells me that the integral converges. As long as you get some finite number, your improper integral converges or is convergent. That's it. Let's box that. That's basically the final statement. Okay? Good. Moving on, find the area of the surface generated by revolving the curve about the indicated axis. So we have y equals e to the x plus e to the negative x over 2. The bounds are x is between 0 and natural log of 2 inclusive, and we're spinning around the x-axis. Okay, so let's remember what our formula is for surface area. 2 pi. And then we have the radius, ds. ds is a little piece of arc length. So it's going to be square root of 1 plus either y prime or x prime. The way it's written, though, I'm just going to assume, yeah, it's y prime squared. Dx in this case, because we're going to integrate with respect to x. Look at how the limits are given. Look at how the function's given. So it makes sense. This is just going to be 0 to ln of 2. Now we have to figure out the radius, and the radius is dependent upon which axis you're revolving about. So if you're spinning around the x-axis, then the radius is y, which in this case is e to the x plus e to the negative x over 2. If I was integrating with respect to y, I would have just left the radius as y, but since I'm integrating with respect to x, I have to replace y with how it's defined in terms of x. Okay, so here we go. That means the surface area is going to be 2 pi times the integral from 0 to ln of 2. Y is e to the x plus e to the negative x over 2 times square root of all of this stuff, dx. So 1 plus y prime squared dx. So why don't we go figure out what this all is and clean it up as much as possible so we're not rewriting the whole stinking integral just to do some algebra, right? And I want to clean it up so that I'm at a point where I can easily integrate all of this. So we have some work to do. Now, if you recognize, this is one of our hyperbolic functions, and you want to use the derivatives and all of that, you can. But you are going to have to go back to the original definition at the very end in terms of natural logs in order to get the final answer, which should be a constant. So you wouldn't leave your final answer in terms of like the inverse hyperbolics is what I'm trying to say. So I don't know if it really saves you that much time. I've done it both ways. I'm just going to stick with this. Okay, let me rewrite y though, because we're going to have to take its derivative. Y is 1/2 e to the x plus e to the negative x, right? So y prime, leave the 1/2 there. It'll be e to the x minus e to the negative x. And then I need to square it. So y prime squared. You have to square the whole thing. So 1/2 will be 1/4. And then if I square e to the x minus e to the negative x, it becomes e to the 2x minus 2 plus e to the negative 2x. Let me clean this up, distribute. This is 1/4 e to the 2x minus 1/2 and then plus 1/4 e to the negative 2x. Now, underneath the radical, I have 1 plus y prime squared. So let me add 1 to all of this. And then the only thing that changes is that negative 1/2 now becomes a positive 1/2. And then the trick is you need to recognize that this is a perfect square trinomial that factors into, that's it, 1/2 e to the x plus 1/2 e to the negative x squared. And hopefully you recognize that because you go, oh, this is exactly the same as this expression here. It's just the minus 1/2 is now a plus 1/2. And where did I get this from? I got it from squaring all of this, right? So then that means this expression here is basically the same thing squared, just switch that minus to a plus. So the only thing I switched was this minus became a plus because this minus became a plus when I added the 1. All right, hopefully you've seen that like a million times already. That's just the one classic move for these surface area and arc length problems. Good, then we can put it all together. So surface area is going to be 2 pi integral 0 to ln of 2. And then we have, again, let me write that instead as 1/2 e to the x plus e to the negative x. And then I have square root of this guy, which let me factor out the 1/2 e to the x plus e to the negative x dx squared. Okay, good. So this square root is going to cancel with the squared. And then notice I just have the same thing twice. So I basically have 2 pi integral 0 to ln of 2, 1/4 times e to the x plus e to the negative x squared dx. And then take the 1/4 out. So we've got pi over 2 integral 0 to ln of 2. You got to multiply this out to take the antiderivative. So it'll be e to the 2x plus 2 plus e to the negative 2x dx. Good. Then we can take the antiderivative term by term. I ran out of space because I'm writing all the steps out. I usually, maybe we'll do some algebra in my head. Okay, so 0 to pi over 2 out front. Let's just take the antiderivative now. So we'll have 1/2 e to the 2x plus 2x minus 1/2 e to the negative 2x from 0 to ln of 2. And then we need to substitute in the limits of integration. So pi over 2 times 1/2 e to the 2 ln of 2 plus 2 ln of 2 minus 1/2 e to the negative 2 ln of 2 minus 1/2 e to the 0 minus 0 plus 1/2 e to the 0. Good. So then this will cancel with the other term. So those are all zeros. And then in order to clean this up, you need to use your logarithm properties. Move the constants to the front. So this is pi over 2, 1/2 e to the ln of 2 squared, which is 4, plus 2 ln of 2 minus 1/2 e to the ln of 2 to the negative second. And then everything else was 0. So this is pi over 2 times 1/2 times 4 plus 2 ln of 2 minus 1/2 times 2 to the negative second, which is 1/4. So then we're left with pi over 2 times 2 plus 2 ln of 2 minus 1/8. So 2 minus 1/8, that's 15 over 8 plus 2 ln of 2. And then I would just distribute the 2 in the denominator, leave the pi out there. Yep, and then you have 15 over 16 plus ln of 2. So good. So good. Okay. How was that one? Little like algebra intensive, but it's just that classic maneuver that you do with all of the surface area arc length problems. So it should be familiar. Okay. Another improper integral. Determine whether the improper integral converges or diverges. We have integral from 0 to natural log of 7, x to the negative third times e raised to the 1 over x squared dx. So again, the first thing we need to do is rewrite this improper integral with a limit, because this lower limit of 0 makes the integrand undefined. We have 1 over x squared, and then x to the negative third is the same as 1 over x cubed. So that'll be undefined at 0. So we have the limit as, pick a variable. I'm going to use t, goes to 0 from the right. And then this will be integral from t to ln of 7, x to the negative third, e to the 1 over x squared dx. You do have to say from which side you're approaching. And just remember, if your integral goes from 0 to ln of 7, the only way to approach the lower limit is from the right. Okay, at this point, there's not too much to do. We're just going to do a u sub. So a little more straightforward integration. Let's let u equal 1 over x squared, which is x to the negative second. And then du is negative 2x to the negative third dx. So negative 1/2 du is x to the negative third dx, which we have right here. X to the negative third dx, negative 1/2 du. Then let's switch our limits from being in terms of x to being in terms of u. So u of t would be t to the negative second. And then u of ln of 7 is just ln of 7 to the negative second. And no, you can't move that exponent to the front. You can only move the exponent when it belongs to the argument here, to the 7. If it applies to the whole logarithm, it's stuck as is. Don't even think about moving it. The math police are going to come snatch you quick, fast, and in a hurry. Okay, so we've got limit. T goes to 0 from the right. Negative 1/2 t to the negative second to ln of 7 to the negative second. And then we've got e to the u du. Everything good? The limits are ugly, but the rest is like cute. Like we can take the antiderivative of e to the u, no problem. So you're like, I'll take those funky limits any day. We got this. So negative 1/2 e to the u evaluated from, you guys, I'm going to do something a little wild. I'm going to make this positive and actually switch these limits. So I'm going to put t to the negative second up here and ln of 7 to the negative second. And then I don't even have a negative out here. It'll help because the less negatives you have, the less chances you're going to make a mistake, especially when you have to evaluate the limit and whatnot. Okay, so limit. T goes to 0 from the right. 1/2 e to the t to the negative second minus e to the ln of 7 to the negative second. Now, just like I told you last time, when you're doing limits and you've got negative exponents, it's kind of hard to imagine what's going on. So I like to rewrite them as positive exponents in the denominator. So write it as e to the 1 over t squared. This one, as much as you may want to clean it up, you can't. I told you this can't move. These don't cancel because of this exponent. So you're just stuck with this ugly little number. It's fine. It's fine. Don't worry about it. So t goes to 0 from the right. Where's 1 over t squared going to go? If you have a constant in the top and the denominator is shrinking, this one's going to positive infinity. For two reasons. T squared is always positive, and also t is going to 0 from the right. So e raised to something getting very, very large, this is all going to positive infinity, minus, this is just some number, okay? My students were like, why did you write hashtag? Back in the day, you youngsters, this was called the pound sign, and we also would use it to represent number. So instead of writing the word number, we would write what you refer to now as the hashtag symbol, okay? But there were no hashtags in my time originally. So we've got infinity minus some constant, some number. So this is still all going to go to infinity. We're multiplying it by 1/2. That won't do anything. It's still going to go to infinity. So that's my final answer for evaluating the limit. It goes to infinity. Well, that tells me this improper integral is divergent. All right, that was it. No L'Hopital's rule. That's good. Okay, number 8, arc length. Find the length of the curve. X equals y to the 4th over 8 plus 1 over 4y squared from y equals 1 to 2. Let's remind ourselves our arc length formula. Since we have a function of y, the limits are going to be in terms of y, and then the derivative is going to be 1 plus dx dy squared, and we're going to integrate with respect to y. Ooh. Okay, so let's, again, like with that surface area problem, let's find the derivative, square it, add 1, clean up, and then I'll put everything together in the integral. So let me rewrite my function. X is 1/8 y to the 4th plus 1/4 y to the negative 2nd. So dx dy is going to be 4 times 1/8, so 1/2 y cubed minus, and then 2 times 1/4, yeah, that's 1/2 y to the negative 3rd. Then let's square it. So dx dy squared is going to be 1/4 y to the 6th. Now don't forget, you have to square the entire quantity, right? Minus 2 times 1/2 y cubed times 1/2 y to the negative 3rd plus square the last one, 1/4 y to the negative 6th. So if we clean this up, it's 1/4 y to the 6th. These cancel, so I just have minus 1/2 in the middle, plus 1/4 y to the negative 6th. Good. Now 1 plus dx dy squared, you should recognize, I'm going to add 1 to all of this. So what changes? Just the negative 1/2 is now positive 1/2. And then I know when I go back to integrate, I have to take all of this and put it under a square root. So I want to see if it'll factor. That way I can make my life nice and easy. And it sure does. Because remember, this matches exactly what dx dy squared was. It's just now we have a positive 1/2. So how would it factor into this squared with a plus? So it's going to factor into 1/2 y cubed plus 1/2 y to the negative 3rd quantity squared. Are we good? Okay, so arc length is going to be integral from 1 to 2. I have square root of all of this, so I'm just not going to write the squared. 1/2 y cubed plus 1/2 y to the negative 3rd dy. And then if I were you, I would take the 1/2 out and then just take the antiderivative now. So 1/4 y to the 4th. 1/2 is gone, so then you have minus 1/2 y to the negative 2nd, evaluated from 1 to 2. It'll just make the fractions not as messy. Instead of 1/8 and 1/4, I only have 1/4, 1/2. A little easier to work with. Okay, now evaluating it. So we've got 1/2 times 1/4 times, this will be 16, minus 1/2, 2 to the negative 2nd, 1/4. Minus 1/4 plus 1/2, and then you can clean it up and you should end up with 33 over 16. Okay, very good. 2 more. It actually ended on an easier note, I think, than some of the problems in the middle. So evaluate the integral. Notice we have like a quadratic function in terms of sign and then just one lonely little cosine. That's screaming to me that we need to do u sub. So let me let u be sine t, and then du is cosine t dt. So this is going to be integral du over, good, u squared minus 10u plus 21. Now from here, hopefully you recognize it's time to find the partial fraction decomp of the integrand. So 1 over, that factors into u minus 7 times u plus 3. Those are both linear factors, not repeated, so the decomp will have the form a over u minus 7 plus b over u minus 3. So clearing out the fractions, 1 equals a times u minus 3 plus b times u minus 7. Let's let u equal 3. Then 1 equals 0 plus b times negative 4. So b is negative 1/4, and then I'm going to let u equal 7. Then 1 equals 4a plus 0, so a is 1/4. okay? So we have now integral 1/4 over u minus 7 minus 1/4 over u minus 3 du. Pro tip, take the 1/4 out. Then you have ln absolute value u minus 7 minus ln absolute value u minus 3 plus c. Wow, right? Isn't that nice? And then just go back, u was sine t. So 1/4 ln absolute value, you need to keep the absolute value because you don't know that sine t minus 7 or sine t minus 3 is always positive. No, you don't. Plus c. And we're done. I would just leave it. You can combine them if you want. I wouldn't distribute the 1/4. Okay, that one took like 2 seconds. Last problem. Evaluate the integral by first performing long division on the integrand and then writing the proper fraction as a sum of partial fractions. So I gave them the hint because remember, it's not time to do partial fractions unless the denominator is bottom heavy, meaning it has a higher degree than the numerator. So in the situation when it's not, then you do long division first. I just wanted to remind them. So here we go. Let's divide x cubed. I need 0x squared as a placeholder plus 4x into 6x to the 4th plus 24x squared plus, let me put 0x plus 4. So just look at the leading terms. What do you multiply x cubed by to make it 6x to the 4th? 6x. And then that distributes. You write the result down here. So 6x to the 4th plus, oh, I didn't put a placeholder for x cubed. Shame on me. 0x cubed plus 24x squared plus, you remembered, didn't you? You've been yelling at me through the screen this whole time. Excuse me. That was just terrible. 0x cubed plus 24x squared. Subtract. Everybody cancels out. Oh no, there's no x. We're just left with 4. That's my remainder because once this degree is lower than the degree of the divisor, you can't divide anymore. So there's my remainder. So I can rewrite this whole original integral as 6x, that's my quotient, plus 4 over x cubed plus 4x dx. Good? Then you do partial fraction decomp on, it says the proper fraction, which is this guy here. Proper because now it's bottom heavy, degree in the denominator is higher. My high school teacher called them J-Lo fractions. Okay, so partial fraction time. 4 over, take an x out, then you're left with x squared plus 4. So the decomp will have the form a over x plus, you need bx plus c over x squared plus 4 because it's an irreducible quadratic. Now let's distribute, clear out the fractions. So 4 equals ax squared plus 4a plus bx squared plus cx. You guys, I'm just solving this exam and going quick. If you need a review on like how the heck is she solving for the partial fractions, I have all the video lectures linked in the description. But I'm not going to like reteach everything from scratch. It would take too long. Heavens to Betsy. So now we're going to solve for a, b, and c, equating coefficients of like terms. There's no x squareds on the left, so that has to equal a plus b. There's no x to the first on the left, so that must be c. And then x to the 0, my constant term is 4. That has to equal 4a. So a is 1. So b is -1. Cool. So then rewrite the integral. So then we have integral 6x plus a is 1 over x plus b is -x over x squared plus 4 dx. Okay, good. Then we can just go term by term. Antiderivative of 6x is 3x squared. Antiderivative of 1 over x, ln absolute value of x. Some people needed to do the u sub off to the side, which is fine. You would let u be the denominator. And then you'd have a 1/2 x, 1/2 du is x dx. So antiderivative is going to be -1/2 ln x squared plus 4 plus c. So if that's not obvious to you, that's fine. Just do the u sub off to the side. I didn't need to see it, but I'd say like it was mixed. Half and half did it, half didn't need to. Okay, that concludes the video. Hope you enjoyed it. Hope you found it helpful. If you're studying for your Calc 2 exams, could you work through all of these problems correctly? Not to say I know what sort of stuff your teacher's going to put on your test, but the more you practice and just expose yourself to solving, especially different integration techniques and different integrals, then the better prepared you'll be. Okay, don't forget to give the video a thumbs up, subscribe if you haven't already, and like I said, I have all of the full-length video lectures linked in the description if you need more explanation, more breakdown. Don't forget to follow me on Instagram, TikTok, Math with Professor V, and I'll be back with more content soon. Bye, guys.